Hi guys, welcome to this, the first in a series of videos that are going to be looking at the course material for the Higher Geography course. Now we're going to start today with our first topic, so we're in Unit 1 and we're looking at atmosphere. Now, in this topic, we're going to be looking at the different factors that influence the amount of solar energy or insolation that makes it to the Earth's surface through the atmosphere, and how this energy gets distributed around the Earth by the atmosphere. Now, largely speaking, there is kind of four areas that we look at in this topic. We've got global heat balance, or the global heat balance. We've got the three-cell model. We've got oceanic currents, which admittedly isn't the atmosphere, but it's very important when we look at how energy is distributed. And then we've got the intertropical convergence zone, or the ITCZ. Now, first things first, and this isn't strictly part of the course, this isn't the kind of thing that would appear in the exam, but this is really important just for setting the scene. So you don't really need to take notes in this bit, but just listen in regardless. What actually is the atmosphere? What is it? What does it do? How is it made up? Now, lovely blue sky. Is this what made the atmosphere? Well, kinda is, yeah. Now the atmosphere is a blanket of gas that surrounds the planet. It wraps itself around the Earth and it does a whole bunch of different things. But some of the functions that it has include providing the correct balance of gases for breathing, so that we can live. It filters out solar radiation. It helps to retain solar insulation or heat so we don't all freeze. It moves heat throughout the latitudes so that we don't just have a couple of bands around the Earth where we can actually live. And it reduces diurnal temperature extremes. Now what that means is really large extremes between day and nighttime temperatures. Now this is a lovely little diagram that just shows you the depth of atmosphere that we're operating on here. So the atmosphere, it goes a pretty long way. We have got 140, 150 kilometres worth of atmosphere. And it's split up into different areas. So we've got different spheres within the atmosphere. The troposphere, stratosphere, mesosphere and thermosphere. Now in between each of these we've got a little bit of a transitional zone that we call a pause. So as you go from the troposphere to the stratosphere, you've got the tropopause. Then above that we've got the stratopause, and then finally the mesopause. Now one of the things that's quite interesting to look at, in that if you go up in height, if we look at this line here, temperature decreases with height. This is something that we're fairly comfortable with. We understand the way this operates. However, you hit a point, once you hit, around about 10 kilometres or so in height, where that then levels off. You stop losing heat as you go up. And then actually, once you get kind of through and beyond the ozone layer, it starts to increase again. Until you hit around about the stratopause, so around about, 46 odd kilometres in height. It levels off again, then it starts to drop until we pass through the mesopause, and then it starts to increase again as you go back into space. Now this isn't trying to say that space is warm, but what we are trying to say that as you go through the atmosphere and you pass into space, the amount of solar radiation you receive is greater, so relatively speaking it's as if it was warm. Now, to move on from that, so that's just a little bit of an introduction. What is the atmosphere? Now, the first actual part of atmosphere as a unit looks at the global heat budget. Now, loads of text here. Now, please remember, one of the big things with these videos, the reason that I do them, is so that you can hit pause and you can scribble things down, you can rewind it, etc., etc. But back to this. Global heat budget, well, simply stated, it's the different amount of usable heat that the Earth actually keeps a hold of. So it forms a balance that if you look at the amount of energy that comes into the Earth from solar sources, from solar radiation, solar insolation, and then you look at the amount of energy that bounces back off the Earth, or the Earth radiates back out, terrestrial radiation, and that's what our global heat budget is. It's the balance between those two things. Now, as I've said, most of the energy that the Earth receives we call solar radiation or insolation. And this is short-wave radiation. Now, it moves through the different layers of the atmosphere, and as it passes through those layers, some of the insulation gets lost. It either gets absorbed by a whole bunch of different things that we're going to talk about in this video, or it gets reflected back out into space. The process of this happening is one of the atmosphere's really vital functions, because by doing this, it helps to make sure that some of the more harmful elements of solar insolation, UV rays, etc., are actually filtered out, and while ensuring that we still get the heat that we need in order to live. Now, really big diagram, lots and lots of information on it. Now, one of the first things that I'm going to say here, one, this strictly speaking is two diagrams. You can kind of almost draw like a line down the middle here, and of energy that comes in against energy that goes out. But this is a neat way to look at it all in a winner. But one big thing that I say here, particularly if you're looking, you're doing additional reading on this topic and you're looking at different texts, etc., the values here are rough. Depending on the edition of a textbook you look at, you'll see that these percentage values change. And when it comes to exams and all the rest, as long as you are in roughly the correct ballpark, you're on the money. So, start at the beginning. We start at the sun. We've got incoming solar energy, solar insolation, 100%, all of it, coming to the Earth, starting to pass through the atmosphere. Straight away, 6% of that hits off different things in the atmosphere and gets bounced back out into space. Now, you might be wondering, what are we talking about? What's doing this bouncing it back off into space? We're talking about things like molecules, bits of dust, tiny, tiny particles that a beam of energy, a beam of solar insolation is hitting and being reflected off of. We keep coming down and through the atmosphere, and we get 20% gets reflected off clouds. So it hits clouds, it hits the water vapour that's in clouds, and it reflects that back off into space. Now in the atmosphere as well, we've got absorption going on. So the atmosphere itself, those molecules, those dust particles, actually absorb about 16% of the total energy that's coming into the Earth. The clouds themselves absorb about 3% of the energy that's coming into the Earth. So that energy never makes it all the way to the Earth's surface. So we total this stuff up. So we've got 20, we've got 6, so 26%. We're at 29%. We are at 39, we're at 45%. Makes it to the Earth's surface. Of that 45%, 4% of it hits the surface and bounces straight back off, reflected back off into space. So we're left then with 51% that actually gets usefully absorbed by the Earth's surface, by the land, and by the oceans. Of that, we get some that comes back off again. It gets bounced back out into space. Now, the huge majority of this is stuff that we're radiating out from clouds in the atmosphere. So of all the energy that the Earth radiates back into space, 64% has came out of clouds in the atmosphere. 6% was stuff that just went straight off the Earth's surface and out into space. And the remaining 15%, so some of the stuff that we tried to radiate out, actually got absorbed and still stayed in the atmosphere. Now, there's a lot of information here, guys. So please pause this video, have a little look at this stuff, okay? Down at the bottom, we've got a couple of transfers here, sorry, that I forgot to mention. So, rising air and conduction, 7% of the stuff that's coming off the Earth, and about 23% is carried by clouds, or two clouds, sorry, by water vapour that's evaporating up from the Earth's surface. Now, when we talk about solar insolation and the gain in solar insolation that we have, there's four main factors that have an influence over how much solar insolation the Earth gets at any one point. The oblique angle of insolation, the distance of atmosphere that the energy has to travel through, the Earth's albedo effect, and seasonality. Now, these are the things that influence how much energy the Earth gets in any given area, and they're going to be the topic of the next video. So I'm going to draw this to a close here, guys. In today's video, we did a little introduction to what is the atmosphere, we talked about what the global heat budget was, and we talked about where different percentages of solar radiation go on their way into the Earth and where they go when they're reflected back out. And in the next video, as I say, we'll be looking at the factors that affect how much insulation the Earth gains in any one point. And I'll see you then.